So welcome everybody to this first technical webinar, and I'm going to present you a bit about diamond technology and growth at Fraunhofer IAF. And what you already see in the first slide are the different forms of diamond we are working with. The left part is something that you wouldn't identify as diamond, but it is. It's nanodiamond. Then we have polycrystalline material and single crystalline material, and the purest form, of course, the diamond grown at Fraunhofer IAF. So before I start with the technical part, I need to thank a lot of people that contributed to this talk. Of course, this is not all done from my side. There are a lot of people involved in the growth section. There is, we are actually two groups doing diamond homoepitaxy. This is my group and Volker Schimala's group. And within these groups, we have some scientists and PhD students, Arne, Julia, Philip, and Christoph. Then from the technology side, this is mainly done in our clean room. There is Christian and Patricia that put a lot of effort in shaping diamond at the micro and nano scale. And we also have a lot of people involved in characterizing our material, be it X-ray characterization or secondary ion mass spectroscopy. Here is Lutz, Mario, Theo. And for the very new topics we are starting to work on, or where we already started, but we are intensifying our efforts. We use a lot of photoluminescence spectroscopy, ODMR spectroscopy, and here Xavier Vidal has done a lot of work also, which is in some part included into this presentation. So let me just quickly give you an overview on what I will show in this webinar. So I will give a very general introduction on the diamond basics and also how diamond is grown in generally and how we do it at Fraunhofer IAF. Then I will show you our equipment in terms of diamond growth reactors. So the machines we have and what they are capable of. Then we will start with polycrystalline diamond that has been done quite extensive in the past. So here I will show a bit about nanodiamond seeding for coating all kinds of substrates, templated growth, and also doped diamond here, especially boron doped diamond as electrodes for electrochemistry. Then we will have a part about single crystalline diamond. Here, again, we grow very pure films. This includes also isotopically enriched films for quantum technologies. We've done a lot of boron and phosphorous doping in the past for electronic applications, but also this doping plays a crucial role for new NV diamond applications, especially for charge stabilization. So we also do nitrogen doping that includes doping with NV centers that will play, or a lot of people believe that this will play a very crucial role in future quantum applications like quantum sensing and quantum computing. And here we're also doing overgrowth of microstructures, and you will see this on the very last part of this section, how this looks like. And as a last point, I introduce you to the diamond technology, which includes diamond etching and also formation of freestanding diamond micro and nanostructures. So this is the roadmap for today, as you can see it, and you can follow it. So you will know when the seminar is at the end. So first, some basics. I guess everybody knows diamond is very famous as a gemstone due to the light refraction. This is not the type of diamond we are typically using in our research because it's not so handy for having such kind of shaped diamond in the reactor. We are working with such plates in most cases, and in this image you see CVD diamond plates, so chemically vapor deposited diamond. They typically have side length from 1 to 8 millimeters. A standard size is 3 by 3 or 4 by 4 millimeters. These CVD diamond plates can be grown either on other CVD diamond but also on so-called HPHT, high pressure, high temperature synthesized diamond. So HPHT synthesis was the first type of diamond synthesis that has been developed. It's mimicking the way nature produces diamonds. So you're putting graphite powder, for example, under very high pressures and have it under very high temperatures, and then it will form such in most cases yellowish crystals. You can also tune this a bit, but they are very often have a yellowish color because they already include a lot of substitutional nitrogen centers. What I've mentioned before, what we've also done quite a lot, and what we're still doing, is we're producing polydiamond plates, and here we can go to sizes up to actually 6-inch. This is 4-inch in that case. The bluish color comes from slight boron doping. So when doping the diamond, you can get different colors as well. So how is diamond grown? Diamond, ideally, or the best diamond is grown on another diamond. So you're just basically increasing this. You're increasing the size of the crystal by adding other carbon atoms to the lattice. So this is a typical diamond lattice, cubic lattice. Atomic distance is about 3.57 angstrom. And so this is very tiny distance, and that's also a reason why it's hard to get atoms like dopant atoms into this diamond lattice. But boron and phosphorus work, and nitrogen as well. So what you do is you're using a plasma, in our case, in chemically vapor deposited diamond, you're using a plasma to form CH3 radicals, you see here, that will attach to the surface. You also have a lot of hydrogen in the reactor, and basically what now happens is a competition in between etching and carbon deposition, because of, the CH3 radicals will also form graphitic carbon, but this will be fast etched by the hydrogen, and after the etching, just diamond remains. CVD diamond is the purest diamond you can get, and the best to control. That's why we use only CVD grown diamond, or only CVD reactors. Temperature during growth is around 700 to 900 degrees. This is important if you want to coat something with diamond. So your initial substrate needs to withstand this temperature. And we are using a microwave plasma to form the radicals. Here is a schematic drawing on how our reactors look on the inside. We have a bell jar surrounding our holder that has the diamond plates, in this case, for example, some single crystalline diamond plates, and there is a ball kind of plasma on top. And this plasma ball is formed because we have ellipsoidal reflectors that look like an egg. So we're coupling in the microwave on the top focal point, and using that, we can focus the microwaves on the second focal point of the ellipse to ignite our plasma. These are our standard reactors. We have 5 of them, and they can grow polycrystalline up to 3 inches. So they offer a sample area of around 3 inch. Can also grow several single crystals there in parallel for sure, but the whole area is 3 inch. We can do boron, phosphorus, and nitrogen doping in these reactors, so they are available. And on the inside, if the plasma is then ignited, here is a single crystal diamond that is further overgrown. Then you see the plasma on top during the process. Also here, again, the different kinds of diamond, boron doped, intrinsic. Then if you have a very high growth rate and a very high amount of methane, you can get like dark diamond as well, because you get graphitic impurities. And on the right hand side is unpolished polycrystalline material. Then we have 3 reactors that are a bit larger, so they can take samples up to 6 inch. One is shown here. So the plasma bell jar inside is inside here, and you see actually here's also a plasma ignited which contains methane. Then so we can cover polycrystalline material from 2 inch to 6 inch, whatever you prefer. Here you can also put several samples in parallel and then end up having several diamond crystals in the end. So these are the pure diamonds you've seen on the very first slide. In these reactors, we can do boron and nitrogen doping in addition to standard intrinsic growth. And I think for single crystalline material, we could put up to, we've tested it with 40 samples, but we could put up to 80 or maybe even 100 samples in parallel of these 3x3 single crystalline chips. And then we have one further reactor. Currently, we're actually building a second one of this type that is for very pure and thin diamond films. Here we can do nitrogen doping and also isotopically enriched growth. And this reactor is constructed in a way that you have a load lock chamber, so you don't need to purge the whole chamber before starting your growth. You can also heat the sample. So typically our samples are not heated, they are heated by the microwave, but here we have an additional heater that keeps the sample under temperature. And the idea why we've built this reactor is to be able to ignite a plasma, as you can see it here. So this is the holder of the diamond. The plasma is ignited, but the sample is still in hold position so that we don't grow directly on this. We can wait until the plasma is stable, until all gases have equilibrated, and then we immerse the sample into the plasma, starting the growth, having it already at growth temperature. And here we can do ultra short processes that allow us to reach layer thicknesses in the lower nanometer range. So this is our equipment we have. And we're gonna start now with the polycrystalline material. For polycrystalline coatings, as I mentioned before, a good approach to grow diamond is to grow it on other diamond. There is a technique called nanodiamond seeding, where you use very small single-digit nanometer diameter nano diamonds to coat your whole substrate with these, and then you overgrow and form a closed layer. This has been done by a colleague of mine already now almost 6 years ago, and we're still using this process for very thin coatings with polycrystalline diamond. For thick polycrystalline diamond, there are also other approaches, but this will give you very thin layers that are pinhole free. And it gives you also an additional opportunity that you can do templated growth and overgrow three-dimensional structures, that it has been done here. So you can use these nice silica beads, for example, then you seed them with the nanodiamonds, you overgrow them with diamond. This allows you to use them, for example, for probing. This has been published. Another thing is if it's boron doped, and this is possible as well, then you can use these colloids on an electrode to increase the surface area and do catalytic applications with that. Also, you can use these individually, as it has been done here on an AFM cantilever. And if they are boron doped, you can even do electrochemistry on the end of this cantilever. And here is actually shown the detection of dopamine on one of these colloids on the cantilever. Apart from that, for polycrystalline diamond, a very common application is generally electrochemistry. I actually forgot to put a cyclic voltammogram here. The benefit of using boron doped diamond electrodes is that you have a very large potential window in water that offers the possibility to detect a lot of different, for example, heavy metals in aqueous solutions. And also diamond is easily to clean, it doesn't degrade, and yeah, it has a very low background current as well. And here we can do dopant concentrations up to 10 to 21, resulting in very low resistivities of about 0.005 ohm centimeter. And we can grow these from few hundred nanometers to several tens of microns, and have also good characterization methods to get good insight in what the material looks like. So I also added one slide here because there was a question before during registration if we've done work on radiation detectors, and actually also now almost 6 years ago there was a project where a standard PIPS detector for alpha and beta counting was developed. You can look up this paper here. We have put a diamond electrode on top of such a PIPS detector. This was also to deposit radiative materials on this PIPS detector and detect basically the radiation. So if you're further interested, please refer to the cited paper. Okay, and this is a quick overview about polycrystalline. So now let's head on to single crystalline material. And as I mentioned, typically these substrates are just around 3 by 3 millimeter, which is also the case here. Sorry for the missing scale bar. So here we do very pure growth. This is shown here. So this is an overgrown sample, actually a HPHT sample that has different growth sectors that will are also visible after overgrowth. With CVD diamond, I used actually this image to show you a few features that sometimes are occurring. Even the HPHT grown diamonds have some dislocations. This sometimes results after overgrowth in forming these kind of structures that are called hillocks. Apart from that, you have the growth sectors. And what you see in the background, all of these images are interference contrast images. In the background is actually the growth that happened on the backside during the diamond growth. So this is not on the top surface. They are already pretty smooth, but we can further polish them and reach roughnesses below 1 nanometer. I think typically it's in the range of 0.4 nanometers. These pure diamonds don't show any luminescent defects. So this is a PL mapping. You have the Raman peak, you have the second order Raman here. And what you very often see for diamond, which is also a huge problem if you want to grow pure, you will get nitrogen doping, and with that you get nitrogen vacancies, and they will be visible here. 638 is the NV minus, zero phonon line, very close to the Raman peak is NV0, and they have a huge sideband. Also, what you typically see in diamond are silicon vacancies, and sometimes in HPHT diamond you also see other luminescent defects. But for CVD, a very common issue is especially the nitrogen, because as you can think of, it's rather hard to get rid completely of nitrogen because it's just everywhere with more than 70%. And even in this vacuum, in the vacuum chambers, it's not easy to get completely rid of it and also have the purified gases. But this is standard pure growth. We're doing this at rates of around 500 nanometers to 1 micron per hour. And now let's move on to also then doped growth. So we can do boron doping. You see here, actually, this is a nicer initial substrate. You still see, it's also a HPHT original substrate. You still see the growth sectors, a few of these small features that may be originating from dislocations, but here is a 10 micrometer, very heavily boron doped layer grown on top. we can reach dopant level of and acceptor levels of 2 times 10 to the 20 on 100 oriented diamond. For 111 oriented diamond, even higher values can be obtained. I have to say that 111 oriented diamond is rather hard to get commercially. We overgrow samples like this and grow a bit ourselves, but we are also struggling with having a huge amount of these 111 diamonds. I will come back to that for the NV doped growth again, because 111 there has a special feature. So for boron doped growth, we also have rather low growth rates of below 1 micron per hour, but yeah, well, as you see from the XRD scan, we can grow this with very high quality. And here again, we have a large reactor available that can do 50 substrates, maybe even more, depending on how much risk you want to take. You can put in more. Also, what we can do is phosphorous doping, which will result in an N-type doping. Here, the growth rate is actually increased. So we have 1 to 2 micrometers per hour. We reach doping concentrations for, up to 5 times 10 to 18. Also on 100, I gotta say, doping efficiencies on 111 are higher. Here you don't see any features in the Raman spectrum. In case of boron doped diamond, you often see this, especially for the heavily doped here. What this shows us is that we get very high quality. For phosphorus doping, what kind of often happens, because the dopant atom is so large, is that you get a graphitic phase in addition to your diamond phase, and this is obviously not what we want. Okay, then now let's move on to nitrogen doping, which is very important for upcoming NV activities or all projects dealing with quantum phenomena in diamond. Here we have several activities. I'm gonna start with growth of whole diamond substrates. So what you've seen before, the 3 by 3 millimeter substrates, we can grow them heavily nitrogen doped by ourselves. We can reach substitutional nitrogen densities of up to 50 ppm. With that, you would end up having a top NV density of around 0.1 ppm. Typically, if you want to get higher with nitrogen vacancies, you irradiate it with electrons. On the left-hand side, what you see is the T2, so that's the decoherence time that is reached in diamond, and diamond is known to have very high T2 times and also T1 times because of its rigid structure. And there is a theoretical model here, the Wadsworth model, that predicts the T2 times depending on the P1 concentration. P1 is the same as substitutional nitrogen. So if you have too much nitrogen in your lattice, the nuclear spin will also influence with the electron spin from your NV minus, and this limits your T2 time. So, but we're on the border of this model, so we're really reaching the highest quality for nitrogen doped diamond substrates. So if we can do large substrates, we can also do thin layer growth. This is actually not so easy as it sounds, because the nucleation behavior of nitrogen doped diamond is a bit different to intrinsic diamond, but we've succeeded in doing that. And what you see here is a typical photoluminescence scan, a depth scan that shows you a thick 100 oriented NV doped layer. In this case, it's approximately 50 microns in thickness. Then here on the right-hand side, this is again a photoluminescence spectrum. Here, the Raman peak is not visible because the luminescence from the NV defects are way higher than the Raman peak. And you see here the NV0 single phonon line, zero phonon line, and the NV minus zero phonon line. And as I mentioned before, the huge sideband. So directly after growth, we end up having this nice luminescent spectrum. What is important here to mention is also that the ratio of NV minus to NV zero is rather high. And this is important because for the quantum sensing applications, you need the NV center to be in the NV minus state. Otherwise, you don't have the electron that can be addressed or the electron spin. And as I mentioned, for 111 oriented diamond here, there is a special feature, because if you grow on 111 oriented diamond and you're using the right process parameters, all these nitrogen vacancy centers, so you will have basically the nitrogen sitting in the lattice, and directly on top you get a vacancy. So this is only possible on 111 oriented diamond. So it's not a 2-atom system, but you have the nitrogen and the vacancy all aligned along the growth direction. And in this case, the vacancy pointing towards the surface of the diamond. And this can be seen if you're doing optically detected magnetic resonance and you use a magnet close to it, that you typically what you would see for each orientation is that you get a dip depending on the orientation of the nitrogen vacancy, actually 2 dips, because they are split by the Siemens splitting and for each state. And if there are only these 2 dips independent from your orientation of the magnet, this means that there is only one orientation visible of the NVs. So in this case, we're seeing a very thin or a rather thin layer, approximately 1 micron on an intrinsic buffer, and also capped with a very thin intrinsic diamond layer. So this is a 111 substrate overgrown. And as I mentioned, we have a special reactor that allows us to grow very or nanoscale thicknesses and isotopically enriched layers. So what you see here is a diamond that is overgrown in alternating ways, first with an intrinsic standard layer, then, for example, an isotopically enriched nitrogen doped layer, and then again intrinsic, and so on. And this is a SIMS profile from this, from such a diamond. So the minimum thickness here we reached was below 100 nanometers. We already succeeded in getting even lower. So even so-called delta doped diamond layers should be achievable in these reactors. Also, what I mentioned before, the nitrogen, the substitutional nitrogen decreases the T2 time in your NV minus center. This is also true for the nuclear spin of 13C. So that's why isotopically enriched films are beneficial for quantum technology applications. Then another technique we are following is overgrowth of microstructures. This has been done before for growth of scanning probe magnetometry tips. You can see a paper published here, and this is data from a paper that will be published soon. What we can do is, this is done in our clean room. You will see afterwards there are such structures, or we can obtain such structures on diamond. This is a pillar structure that is overgrown in our reactor, and in a way that only the structure is grown further. So basically we are forming these pyramidal structures with clear 111 facets. And these clear 111 facets allow us to dope nitrogen vacancies, but also also silicon vacancies, for example, only into these 111 facets. And this is what you see here on this PL map, laterally resolved. You see that on the top, even there is no growth happening with a nitrogen doping. You only have PL luminescence on the sides. And this is not shown here, but I can tell it to you on these 111 facets. Also, the NVs are oriented along the 111 axis. So in this case, this would be the 4 111 orientations that you would have. Okay, and then for the last point, a little bit about our technology. So we're typically doing inductively coupled plasma etching with different kind of masking. We have electron beam lithography, we have laser lithography, and in this case, we can also do de-wetted metal masking. So this was done before for boron doped diamond electrodes in a very recent paper to reduce carbon dioxide. So what you see here is a typical polycrystalline boron doped diamond sample already with the small droplets of a metal mask after de-wetting. And after etching, you end up having this nice nanoscale. So this is 200 nanometer, and the structures themselves are around or below 100 nanometers, rather deep, giving a large surface improvement. And this is, of course, beneficial for electrochemistry because there the reaction takes place only on the surface. Also, what you end up with, this is actually a photograph of boron doped diamond wafer. The wafer normally is a grayish color. After the nanostructuring, it is deep black. Then we are also doing this on single crystalline diamond for sure. And as I mentioned, we're producing tips for scanning probe magnetometers, which is a very recent field. Actually, there are, I think, only a few companies, probably 3 or maybe these days 4, that can provide you with a scanning probe magnetometer. There you have these pillar shapes here, as we've seen before, that we've already also overgrown. And in this pillar, there's a single NV center integrated that acts as a sensor for the magnetic field. And by rastering this over the surface, you can detect very small magnetic fields at a very high lateral resolution. So this is one approach where we are doing standard etching from top. And we have another technology just rather recently realized, which is called Faraday cage angled etching. There you're using a Faraday cage around the sample, and this allows you to obtain such freestanding structures. Here, Christian Giese has published a paper recently, and you can look that up if you want to know more. So this allows you to produce photonic structures, like, for example, such waveguide structures that are completely freestanding. Here, actually, even this whole structure can be taken off the initial substrate. And what we've done is we attached it to a tuning fork to do AFM measurements with it. And another step then would be also to integrate nitrogen vacancy centers in such structures. And with that, I'm at the end of my presentation. And I hope that you got a bit of an insight into diamond technologies at IAF. And if you're planning to submit a proposal, either contact us directly or use the inquiry form on the ASCENT Plus webpage. There's also a link here and a QR code. And if you have any further questions right away, then please do not hesitate to ask now.
Thanks very much, Peter. That was a very interesting talk. I hope everybody found it interesting as well. Before we go into the Q&A session, I just want to remind you the way, as I was saying earlier, this is going to be a series of webinars presenting the ASCENT Plus offerings. So there'll be one on the, I think it's the 27th of April. There'll be one presenting the gallium nitride ICs that are offered by IMEC. I don't know. Can you share, Paul, or can I try to share just to have to? Oh yeah, thank. Yeah. No.
If Peter can unshare first.
Oh,
yeah.
Sorry.
There, now you should be able to share, or I can share, whichever you like.
Yeah, you can share it, Paul. Yeah.
Okay.
It's just quicker.
Right.
So this is just a reminder. So yeah, it will be on the 27th of April. It's a Tuesday, and it will be the gallium nitride IC offering from IMEC. And the same as you did for this one, you'll be going to the same page in the website to register to attend. So we can go now if you have any questions. I think Peter already answered the question we got to registration about the using it for radiation sensors. So does anyone have any questions? So if you do, please turn your microphone and your camera on and ask the question now, please.
I think there was also a question in the chat concerning co-doping with nitrogen and phosphorus. So generally that is possible. One issue there is that for phosphorus doping, we are using a precursor that is rather easily cracked. And nitrogen, on the other hand, needs a bit higher energies to be cracked to be then included in diamond. So for low doping concentrations with nitrogen, it is possible, but it's a process that is rather hard to control, actually.
Very good, thank you. Any other questions? As I was saying, you can turn your microphone, your camera on, or if you are happier just to submit it by the chat, that's fine as well.
Yeah, I have a question actually.
Hi.
Yeah, hi Peter. I have a question about the doping in nanodiamonds powders, like not on the films, but in case of nanodiamond particles. So I know that we can use some ion implantation process and all for doping impurities to the nanodiamond particles, but how does that work? Like it's powders, so there will be some repelling, forces to when we are implanting with the high energy ions. Is it really efficient, or how does that work? Because all these methods, whatever you explain at the moment, is during the growth itself, we are adding some impurities to the chamber, and is that right? If I'm not.
Yeah, that's right. Maybe concerning the implantation into nanodiamonds, I think, this is a rather difficult task, but it's doable. Other groups are doing that. We have done a bit of work in the past by also introducing dopant atoms by overgrowing such nanodiamonds. Of course, then you will end up having a larger size of the nanodiamond ultimately, and also depending on what kind of growth you proceed, it's rather hard to get them off your growth substrate again, because it's a powder that will probably stick to the surface. So does that answer your question?
Yeah, that's fine. But I'm still looking for like, how can we make it more efficient when we are doing this ion implantation process on nanodiamond powders? How can we make sure that it is completely going to work out and they're not going to, waste those nano powders?
Yeah, this is for me hard to say. We're not doing a lot of implantation actually.
All right, okay. Yeah, that's fine. Thank you.
Thanks very much. Any other question? There was a question in the chat, but was more about the webinar access itself. So I just replied there. It is still recorded, so we'll be uploading the video and you'll be able to access from the website. If you have any colleagues or any friends that couldn't attend today, you'll be able to watch it, watch the recording. And for the questions, the same. If you have any questions now, great. But if you can think of something in the next few days, send it to us or to Peter, and we'll reply by email or offline. Any other questions? Okay, I think we can leave it like that. So, and as I was saying, contact us as Peter said. If you have any interest on these technologies or any of the other offerings from ASCENT, through your website, you can submit an inquiry and we can deal with it directly with you, or you can talk to Peter if it's specific to the diamonds. And hopefully we'll see you soon, and hopefully ASCENT will be able to help you with your technology needs and requirements. So thanks again to everybody for attending, and thanks to Peter for, I personally found it very interesting. It's an area I don't know much about, the diamond technology, so it was I learned quite a lot. So thanks again to everybody, and hope to see you soon next month with the next one of our webinars. Thank you. Take care.
Yep. Thanks to everyone.
Thank you.
Thanks, Peter.
Thank you.